All right, so what we've done so far is looked at groups, and you had to do the, let's see, what was it? Closed, associative, identity, inverse to prove a group. For the subgroup, how did we prove for a subgroup? There were like two things there, weren't there? For a subgroup, it was that A-B inverse, remember? A star B inverse. That was the sticky part. And then the identity had to exist. So you had to find the identity and check for AB inverse. And then we had cyclic groups. With cyclic groups, you just had to show that the order of one of the generators was equal to the number of elements n. That's how we prove that. Now what we're going to look at is something not too complicated, but it can get more complicated symbolically. And that's the idea of functions dealing with groups and subgroups. In other words, let's say we took G and H. G has a different operation than H. And we were somehow going to do a composition of those. And so we're really talking about a composition of functions dealing with groups. Okay? And so what a homomorphism is going from G to H. Think of G as the inside of the function, and H is the outside. Okay? To prove that it's a homomorphism, you have to show that f of a star b equals f of a with the other operation, the h operation of f of b. That's the biggie for this one. And then kernel range and isomorphic is the kernel of f is the value of g that makes the, I'm just going to write it, value of g that makes identity of h. Or if we're talking inside, outside, the value of the inside of the function that makes the identity of the outside of the function. The range is just looking for that one-to-one, or we called it onto function of the function. That'll show the range. Oh, I'm sorry, I jumped ahead here. This is for isomorphism. So this is just the range of h when we look at R of f. And then isomorphism is that your function f is one-to-one. That's it. That's it for kind of the bulk of this section is going to be here. Do you have this blocked out on yours? I hope. Is it? Good. I saved it this morning. It says, for the two given groups, determine whether the function is homomorphic. If it is, find the kernel and the range and whether it's isomorphic. So this is my main goal today. If we can get this, whew, doing awesome. All right, we're starting with the real numbers in the plus, going to the real numbers in the plus for the function 3x. So this is my g, and this is my h. And we're putting it into this function 3x. All right, so let's look at the first part, f of x plus h. So what we want to show is that f of x plus h is equal to f of x plus f of h, or f of x, f of y. That's what we want to prove. Will that work for 3x? If we go 3 times x plus y, is that the same as 3x plus 3y? Yeah. So then we can say for all of those, So this is f of x, this is f of y, f of x plus f of y for all x, y is an element of R. That makes sense, doesn't it? It's not too bad. So we're analyzing these groups with the context of a function. Homomorphic. F is homomorphic. You love kernels, right? Remember how much fun we had with linear and those kernels? Blah. But all the kernel is if you put into your function, which was 3x, right? For addition, what's the identity? 0 or 1 for addition? 0. So what would x have to be to give you 0, the identity? 0. So for this one, if the identity is 0, the identity for the second h function would also be 0. So the kernel for this one is 0. It's the value you put in for x to make 0. Love that for a first one. Range is all reals. If we draw a graph, 3x, are all the y values represented? So it's all reals. Write that down, and then it's 1 to 1. Does it pass the vertical line test? Does it? Does it pass the horizontal line test? Yes. And yes. So therefore, it's 1 to 1 and on to, therefore it's isometric. Isomorphic. Think you could do those? Think you could do that? Show that, write those things in, write the steps. So what you start with is you want to go f of x plus h equal to f of x plus f of y. That's what you got to prove. If it isn't plus, maybe it's multiply. So if this is multiply, it'll be f of x times f of y. We'll see what happens with that. If that works, then it's homomorphic. Find that kernel, find the range, and see if it's isomorphic. All isomorphic is 1 to 1 horizontal vertical line pass for isomorphic. Just a quick explanation of this part B. We're trying to show that f of x plus y equals f of x times f of y because we're switching operations in B from plus, try that again, from plus to multiply over the function 2 to the x. Okay, so what we did then, is we use the property 2 to the x times 2 to the y, which is f of x times f of y. Don't forget to write for all x, y element a real. Would you do that? Both of those were reals. But notice that this one goes to the real positives. So we're going to deal with that in a minute. Okay, so it's homomorphic. Now for the kernel is going to be 0 for addition, right? What will x have to be in order to get 0? So here's what we're doing. We're looking at, was it 2 to the x, right? So that's my f of x. We want for addition that to be 0, but when we put a 0 in for x, we get 1. So for the function, the identity is going to be 1, and then x will have to be 0 to get 1. That's a good one. It really makes you think a little bit for identity. The kernel is 0. That's the value for x that will get you the identity 1 for multiplication. And then for e to the x, you remember e to the x. What's true about all the e to the x values? They're positive, so that's why r is positive. What do you think about, is it 1 to 1? Always increasing, so it's isomorphic. Good. Last thing. Last part. So there's a couple of theorems that you're going to want to put in here. One is, would you go to theorem 21? And I think they were using that in that problem. F of E of G, this is the identity of G. When you put that into F, will be the identity of H. In other words, E of G is the kernel of F. So they're going to prove that. And the way they proved it, they let A be an element of G. And then since it's homomorphic, you're saying it's homomorphic. So therefore, you can say F of A operate F E of G. And F of A, because it's operated on the identity, should be equal to those two, F of A times, or operate F E of G. Since F of A is an element of H, and we can replace F of A with H, and it's a group, so the inverse exists. So we can have H equal to H of F inverse, multiply both sides by F, operate both sides by H inverse, and then H inverse of H, operate this will give you E of H, and E of H, operate that will be F E of G. So that's how they did it. I kind of see how they do it, but they're just saying that the identity element of H is F of the identity of G, and that's the kernel, essentially, gives you the identity of H. One more time. Kernel of F is going to be E of H. That is what they're saying here. And then this one, F of A inverse equals FA inverse for all A in the group. That's because of the group nature. And you can see that proof. Actually, you can't. They proved that one. I'm not going to go through it. I couldn't follow it in a couple of spots. But what they're doing is they're saying since it's a group, you can put the inverse to both sides. A of G equals A inverse. That's what the identity of H is. And so when they took the function of both sides, these are equal from the previous. And then those two together will show that the inverse will give you F of A inverse equals F of A inverse. So kind of a yucky thing, but don't use that one very much. Homomorphic injection, we talked about that, is an injection if and only if the kernel equals EG. This is a substitution that you can make. If you do find the kernel is equal to E of G, where E of G is an identity of G, then you can make a statement about it being an injection. We just use graphs for this. And then the last one is talking about groups themselves. If G operated on H is homomorphic groups, the kernel is a group, subgroup of G, and the range is a subgroup of H. So kernel of F, which we said was E of G, is a subgroup of G, and the range of F is a subgroup of H. That kind of makes sense, doesn't it? Kind of makes sense. They'll prove those. For tomorrow, I want you to do D and E, G, I want to say